Good morning, everybody. Today there's the Codeforce's Qualification Round, so it's more of like a mandatory practice than anything. Well, I guess not quite. You do have to solve 30 points, which looks like that's at least, well, it's either a hard problem or two problems, or maybe even more than that, depending on which ones you solve. So I'm going to be solving that here. I've got 10 hours left, so there's no rush, although it is pretty late. Or early, I guess, depending on what you want to lay. It's like 2 a.m. I just took a nap before this after work, and now I'm like, yeah, I don't want to like go to sleep and then run out of time tomorrow morning, so I'm going to do it now. But here we go. I'm going to be using, well, I've got my shirt for my favorite search engine, and then I've got my browser for my favorite web browser. Mozilla Firefox, DuckDuckGo, which is the search engine that I use and fully support because they don't run silly contests that are only for people of specific genders. I feel like that's kind of a bad thing to do. But CodeJam, like the regular CodeJam at least, is a pretty upstanding contest run by some good people. So I'll do that. And since I'm going to be taking it seriously, I'm going to try and get to the finals this year. I guess I'd be pretty lucky if I ended up qualifying for the finals, but I want to try it. So I'm going to be using Java for CodeJam this year. So I'm not going to be doing any Kotlin for it. It's just going to be Java because I'm going to be taking it seriously. All right, I haven't looked at any of the problems, but I guess looking from the scoreboard, it looks like it shouldn't be too difficult to solve them. I guess maybe they get more difficult as we go on. But yeah, just like kind of like Facebook Hacker Cup qualification rounds, I don't really know whether I want to solve all of them tonight or just solve enough in order to get my 30 points. So yeah, I guess we'll start going here and then see where it goes from there. All right, reverse sort, and then there's reverse sort engineering. I see. What is reverse sort? Oh, gotcha. Very cool. Reverse sort is an algorithm that sorts a list of distinct integers in increasing order. The algorithm is based on the reverse operation. Each application of this operation reverses the order of some contiguous part of the list. The pseudocode for the algorithm is as follows. For I is 1 to the length minus 1, get the position with the minimum value in L between I and length inclusive. And then reverse it. So, okay, yeah, that makes sense. So if you've got something like come on. All right, so if we have like 5, 2, 1, 3, 4. If we get this is the index of the minimum, and then when we reverse it, we move 1 to the beginning, right? So it'll move 1 to the beginning, 2 to the next position, 3 to the next position, etc. I guess they give you an example here. The most expensive part of the algorithm is the reverse operation. Is it? Not if you use a treep. Anyway. Therefore, the measure of the cost of each iteration is simply the length of the sublist past reverse. The cost of the whole algorithm is the sum of the costs of each iteration. So okay, so 4, 2, 1, 3. Let's do this example, make sure we understand it. So initially you reverse these three, so 1, 3, 4, wait, 4, 2, is it 2? Okay, and then you do this, and then you do these two. So it's 3 plus 1 plus 2. That's equal to 6. Good. All right, so this should be pretty easy to implement. Should just be a matter of finding the smallest thing. So here we go. Multi-test case. Compute array size n. I guess let's start with 0 to n, and then so we want to find the index of the thing we're looking for, and then we want to reverse I to the end. So this will copy the array into the orig array, and then we want to do the same thing again, I guess. You can probably do this all in one line if you're smart. I, however, am not smart, so I don't need to worry about that, right? So this case a at j equals orig at orig.length minus 1 minus j minus I. Good. So this will reverse it. We find it, then we reverse it, and then we need our total. So int total equals 0. Total plus equals orig.length, and then print total. And because Google is like they are, we have to do the silly case stuff. Look at this nice copy button. Well done, well done. Okay, what am I doing here? Negative size index minus I. I guess start at position I, right? That's how it works. I am too big by 1. Yeah, because this needs to be I plus 1 less than n. And then test case needs to start at 1 less than or equal to t. Okay, good. So that's the solution. If we are submitting in Java, I think we need this to be oh, look at that. That's nice. Okay. Let's just give it their tests, please. And then, can we name it A? Is this allowed yet, or no? Compile time error. Okay, so what if we do this? completed. I guess that's what we're going for, right? Cool, so that's this is problem A. We should have a solution there. For the temp class, we want to go from 1 to less than or equal to t. I think that's good. All right, cool. So we've passed this. We've got 7 points. It's not enough. Let's get some more. Maybe we'll go to this reverse sort engineering since it's similar enough. Okay, so we've read this part of the problem. We're here. Okay, so now, gotcha. You're given a size n and a cost c. Find the list of n distinct integers between 1 and n such that the cost of applying reverse sort to it is exactly c, or say there is no such list. So n's up to 100 because we're big boys and we want to get all the points. Both visible, okay. So yeah, so I guess let's think about this for a minute. If we have some like array, if we've got, let's say we have 4 spots, the minimum cost is going to be 3, right? If we have a 1 here, 2 here, 3 here, and 4 here, so it's 1, 2, 3, yeah. So that's the minimum. The maximum it could be is we might need to select the entire array every time. So the min would be 3, which is equal to n minus 1. The max is equal to n plus n minus 1 all the way down to plus 2. Right? So that's equal to n times n plus 1 over 2 minus 1. Yeah. Okay, so that's the minimum and maximum it can be. We had the answer for the previous, so like if you have like, yeah, if you've got the answer for a smaller array, you can plug the answer in for you here as well. So if you've like go of like n equals 5, k equals 7 or something, 1, 2, 3, 4, 5, then we can subtract we can subtract like some integer here. So okay, so what happens? Let's say we place it here. If this is the minimum element, after that we'll have 4 elements, and then we want to reverse the first 2 and then place us in this position. Yeah, okay, so we can make our decision in order 1. And then each time we do this, like we'll have order n recursive calls. Each call is order n. So our runtime here will be n squared, naively. And we have 100 test cases, so runtime should be fine, I think. Yeah, so we should be good there. Cool. Awesome. So we have n equals this, k equals this. Alright, so if k is greater than, if k is less than n minus 1, or k is greater than n times n plus 1 over 2 minus 1, return false, then it's going to be impossible. Or return, I guess, null. Alright, so base case of the recursion, if k is equal to 1, then return just this min array. Otherwise, we're interested in the next array. Okay, so int to subtract, there are a couple cases. So yeah, we want to know, we don't want to subtract too much here. So in the future steps, they're going to need at least n minus 2. Okay. So this is how many we want to subtract. Okay, so now we have the int array next array equals go n minus 1, k minus real subtract, and then min plus 1. So this is the smallest element in the array. Good. So now we just have to copy this array into toReturn. And then real subtract is the position that we're interested in. Okay, so toReturn at real subtract is equal to the position that we want to place. Then we want to place everything after it in the right order. So for int I equals n minus 1, I is greater than real subtract I minus minus. In this case, toReturn at I should be next array at I minus 1, because it's one smaller. And then for int I equals 0, I is less than real subtract I plus plus. In this case, toReturn at I equals next array at real subtract minus 1 minus I. Okay, I think we're good here. So in this case, minimum is 1. Okay. If res is equal to null, print this, otherwise print this. Okay, so in this case, impossible. In this case, we print them space separated. Cool. Let's see whether this works. So toReturn is going to be size 2. Next array is size 1. This isn't k, this is n. If n is equal to 1. I'll real subtract minus 1 here, yeah. okay. Yeah, okay. Maybe we should just subtract 1 from this. Maybe that makes sense. This is the index of the special item. And then we do our flipperoonie. Okay, 4, 3, 2, 1. Does that have 6 operations? No, it does not. So the first step, how many operations do we need? 4. Yeah, I think that makes sense. So that's 4. Oh, 4, 1, 1. Yeah, that is right. Okay, cool. 7, 12 operations. 7, that's not right. It's nice that we've got this test case for us here, right? So if we have one test case, it's 7 big, and it looks like this. It does take 12, really? Does it? I guess it does. Yeah, okay. So I think we might be right then. Let's just verify this first solution. Yeah, okay. Cool. So let's try submitting. This should auto-select. That's kind of annoying, but that's fine. Okay, so that is problem C. Let's wait and see what we got. Looks like we got it right. Very cool. All right. So 5 problems. That's a lot of problems. How many points do we have? We have 7 plus 7 is 14 plus 11 is 25. So 25 plus 5 is enough. So we just need literally anything else is fine. And we've got a visible small test set. So I think that's what we're looking for. So we'll read this here. And that's all we need. And then we can read the other problems, and if we like them, we can solve them. Otherwise, we can not worry about them. All right. Cody Jamal is working on his latest piece of abstract art, a mural consisting of a row of waning moons and closed umbrellas. Unfortunately, greedy copyright trolls are now claiming that waning moons look like the uppercase letter C, and closed umbrellas look like the letter J, and they have a copyright on CJ and JC. Therefore, each time CJ appears in the mural, he must pay X, and each time JC appears, he must pay Y. He's unwilling to let them compromise his art, so he will not change anything already painted. He decides, however, that the empty spaces can be filled strategically in order to minimize the expenses. For example, if it's this, blah, 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 you could finish it in a bunch of ways. Yeah, so just delete all the question marks, right? So here you have a JC, and that's it. Oh, CJ plus JC. Gotcha. Here you have some other stuff. Yeah. So the strategy here obviously is you just take each question mark and replace it with the thing in front of it, which is the same thing as just deleting all the question marks. So we can just ignore every question mark and then count the cost here. That should be pretty easy. Let's speed run that real quick. Are we gonna run into issues with costs overflowing ints? Probably not. All right, cool. Ooh, cost can be negative. Hang on a minute. Okay, so yeah. Cost being negative is a bit of an issue. Okay. If costs are negative, that's tricky. That's really tricky. Okay, what do we do if costs are negative? Then we might want to do that. Well, if costs are negative, we can just do a DP, right? All that would matter, so suppose costs are negative, then what matters is like if we're at DP at some index and then like what its value is. This is going to be equal to like maximum, or I guess minimum cost. Yeah, so what are our choices? We can place a C or place a J at each position. Yeah, and then we've got associated costs with each of them. Cool. To by line.length plus 1. We're going to need a sentinel value because things can be negative. All right. So I is less than dp.length, I plus plus. I type -1 because I'm so, it's like muscle memory, but anyway, okay, we probably also want x and y to be global too. Okay, and then our answer will just be the DP call. Yeah. So int equals math.min of goes 0, 0, and go 1, 0. So if we've already calculated the answer for this pair, just return it. And then we should print the answer here. What if we haven't calculated it yet? Well, if this thing, okay, so if line at index is not equal to, yes, okay, so the base case here is if index is equal to line.length, then return 0. Because like this is, the line's over anyway, so we're not going to incur any more cost. Otherwise, a few things could happen. Yeah, okay. Otherwise the DP might be fixed. Okay, so we might not have a choice here. So if line at index, what is this? I guess this is last, right? Or this is what we've placed here. Yeah, brute force what we place next. For on the last character it's 0 as well. Okay. Yeah. Okay, so if this is not equal to question mark, then we might not have a choice. So okay, let's say if it's equal to a C and placed equals 0, or the other combination of illegal things, which is it equal to J and placed is equal to 1. Wait, no, I have that backwards. So if we placed a J, but it has to be a C, or vice versa, then we place something illegal. In this case, we want to return a very big number. So this is super undesirable. Okay. Otherwise, what we placed is legal. So otherwise, brute force next. Okay, so place is 0. Then return the answer at the end. Cool. So we can place a 0 or we can place a 1. What happens if we place a 0? So best equals math.min of best and something else. Okay, so we might have to pay this cost if we didn't place a 0 last time. So placed is not equal to 0. If it's not, and we placed a 1, 0, then we have to play y, I think, otherwise we pay 0. Yeah, so JC pays y, right? Yeah, JC is y. Gotcha. Very good, very good. So in this case, we just placed a 0, and then we're at index plus 1. Okay, if we place a 1, then if place is not equal to 1, then we have to pay x, otherwise we pay 0. We will have placed a 1 here, so we place a j. There we go. Yeah, we print the minimum. It's always possible. We should always get some number. I think that's the answer. Let's verify here. 5. Okay. I guess maybe this one is 10, not 6. Why 6? Interesting. Multi-test case, huh? Really? Okay, that's fine. All right, so we're saying the answer to this is 6, but it shouldn't be. It should be 4 plus 4 plus 2. Oh, yeah. So this needs to be after this here, because if we play something illegally, we still need to pay the penalty. We're saying we can place CJCC, but you can't. That's not allowed, obviously, right? Because the last thing has to be a J. Good. Run everything one more time. 5, 10, 1, 0. Cool. This should handle negative costs. We can just modify this last one real quick to test that a little bit. So let's say it's -2, -5. I suspect they'll do something like JC, JC, JC. So how many times do we pay -5? So once, two, so -15 plus 4. -15 plus 4 plus -4 is -19. So this last one should be -19 now. Good. All right. So let's submit this. Rename it to solution. Man, this is scrolling. Hello. Hello. Come on. I'm trying to like scroll up and down on this. It's very laggy. It's like the inputs are getting lost or something. I don't know what's going on there. Cool. Let's try submitting that. And we'll see. All right, looks like we got the first two cases at least, which are the easy ones for sure. Extra credit. Do we get any points for that? Oh, 1 point. Okay. Yeah, sounds good. All right, so there are actually 5 problems, yeah. Let's maybe look at these last 2, just for fun. Not because we need them. We should be fine, I think, right? We should definitely have the right number, at least as many points as we need. We have 42 points, optimistically. Yeah, so worst case we have 41 points. We have between 41 and 42 points, I think. Oh, there are 101 points total. Neat. Yeah, okay. All right, medium sort. Median sort it is. You want to sort n distinct items. Unfortunately, you don't have a way of comparing 2 of these items. You only have a way, given 3 of them, to find out which one is the median. That is, which one is neither the minimum nor the maximum among the 3. Suppose n equals 5. Or you also know that x1 is the median of x1, x2, x3. Gotcha. Yeah, okay, I think I understand. So if x1 is the median of these, x2 is the median of these, x3 is the median of these, then it's guaranteed that the sorted order of the elements is one of these. Okay. Your program will have to find the order of t-lists. Okay, so just a bunch of test cases. N elements using at most q median questions in total. Or q over t queries per list on average. In each case, finding either the right order or its reverse is correct. So you get 300 tries for 50 elements, or 170 tries for 50 elements. Interesting. They guarantee it'll be randomly ordered. And this is their interactive problem, of course. Yeah, gotcha. Yeah. Cool. Oh, and then you confirm it's correct or not. I see. Interesting. So there are a bunch of things we could do here. Let's go to the drawing board and think for a minute. Okay, so if you have like something like this, you have some additional element that you want to insert. You want to see like where is its relative position. Yeah, so suppose you have 3 elements, you insert them like this for your first 3. Now you want to find where does this one fit. You can find its position in log n moves. Yeah, you can binary search for sure. Yeah. But this isn't very helpful because, like, what is log of 50? Like 8? Oh, 6. So we take us 6 moves to figure out where we get put. Oh. So that would pass test case 2. We need to do better than that for test case 3 though. Yeah, so you can pass test case 1 without the binary search. You can do the binary search, that'll pass test case 2. But for test case 3, you have to do something even better. Oh, it's kind of annoying. Okay, yeah, so what can we do that's faster than a binary search each time we want to insert something? We could say if we have 2 lists, maybe we can merge them. Let's consider like the first element here, and then second element here. If the median isn't one of the first 2, right, so if the median is this, then we know this one definitely comes first. Yeah, so we can merge 2 lists pretty quickly. We can figure out which one of these 2 elements is smaller. Do we have more information than pairwise comparisons? Probably. We probably get 2 free comparisons here. So I think we have to use it better than comparisons, because I think you need n log n comparisons to sort an array. They guarantee t is equal to 100 though, so we just need to, like, on average have a good solution. Like, we need to optimize for a randomized case. It doesn't need to be particularly strong or, like, particularly difficult to break. If we do 2 queries, we have all the smaller things and all the bigger things. Yeah, okay, so for 2 queries, we can get the relative order of 4 elements. Or we might have it backwards, though. Yes, that isn't super helpful. I'm not sure. This part 3 is kind of difficult. This test set 3 hidden verdict is kind of tricky. I'm going to consider just cheating detection instead, and then go back maybe. All right, 100 players are competing in a 10,000 question trivia tournament. The players are numbered from 1 to 100. Player I has skill level SI, and question J has a difficulty level QJ. Each skill level and question difficulty are chosen uniformly at random between -3 and 3. Okay, independently. For example, a player with skill level of this and a question may have a difficulty of this. When a player tries to answer a question, the probability that they will answer it correctly is this sigmoid function. Okay. Oh, sigmoid of that. I see. There is one exception. Exactly one of the players is a cheater. The cheater is chosen uniformly at random from among all players and independently of all other choices. The cheater behaves as follows. Before answering each question, they flip a fair coin. If it comes up heads, they do not cheat and the rules work as normal. If it comes up tails, they secretly look up the answer on the internet and answer the question correctly. Formally, they decide whether to cheat at random with a 50% probability for each question, independent of all other choices. The rules of the tournament consist only of the per question results for each player. Apart from the general description above, you do not know anything about the skill of the players or difficulty of the questions. You must identify the cheater in at least P% of the cases. So you have to get the cheater right in 86% of the cases, or at least 10%. Pretty vast difference, I feel like, but anyway. How many questions can we ask? 100 players, 10,000 questions. Do we get, is this interactive? Not interactive. What? Yeah, what's the input? The first line of input contains the number of test cases. Second line of input gives the percentage of test cases that you must answer correctly. Each test case consists of 100,000 line characters. The jth character of the ith line is 1 if the player... Ooh, this is a fun question. Okay, so we're given... Wait, does each player answer each of the questions? Gotcha. So each player answers 10 to the 4th questions. We want to identify the player who's cheating. All right, so the first thing we want to do here, this is a really cool problem. All right, yeah. So I have some ideas for approaching this. I feel like we can probably hit test set 2. But let's look at Wolfram Alpha to see what the sigmoid function looks like. So if it, yeah, so, oh, so it looks like it is pretty close to 50%. We can download it. So nice, gotcha. All right, so we probably want, yeah, okay, so what do we want to do here? It's probably helpful to find the difficulty of each question. And then we only want to look at like the difficult questions. The players that get an abnormal percent of the most difficult questions right are probably the tricky ones. Yeah. So a player who's getting like 50% of the easy questions, or like, yeah. So cool. This is way more fun of a problem than D. I really like E. It's super interesting. I don't know how good we're gonna be, but yeah. So the general approach here, is it one test case? Multi-test case. Okay. So we're going to do something like find the difficulty of each question. Then, like, the cheater is either going to be someone, like, suspiciously good, or they're going to be just decent at the hard questions, but like suspiciously bad at the easy questions for how smart they appear. Right? So like it's possible that there are just some really smart people out there, right, that get 50% of the questions right, and then it's possible that despite getting 50% of the questions right, we just like suck and we're terrible, right? If we're the cheater, if we're like really dumb, then we might only get these right like 50% of the time. So we might be about as good as like a smart person, even if we cheat. But if that's the case, we're going to be getting lots of easy questions wrong when we shouldn't be, right? As someone who's good, we should be getting some of, like, we shouldn't be, that shouldn't be happening. Yeah. The good people should be getting the easy questions right, and then the hard questions wrong. And then the cheater will have a very suspicious way of doing that. Do we want to do this mathematically? Do we want to, like, mathematically say, like, the suspicion of getting some question right or wrong? It's suspicious to get an easy question wrong or a hard question right. Yeah, maybe we'll just try whoever's really good at the hard questions first. Because that's a decent strategy. Like, of the very difficult questions, the infinitely smart people will have a 50% chance of getting it right. And even if we're really stupid, we'll have a slightly higher than 50% chance of getting it right. So in theory, we should probably, like, if these numbers were all infinite, this should be, like, the right answer. Then we can do some optimizing after that, maybe. Okay, so this number we don't care about. This next one is just worthless. We have 100 people and 100,000 questions. No, not 100,000 questions. Not very many questions. Only 10 to the 4 questions. This should be n people. All right, good. So we have all of the people. Let's read this in. Input I equals the next line. Oh. Yeah. Okay. So int times right. So we have how many times we get it right. Wait, can you submit in Kotlin? Is that even allowed? I probably should have checked. You can submit in Kotlin. How nice. Okay, fun. You can submit in a lot of stuff. Wow, I'm impressed. Okay, anyway. So we also probably want the index here. And then this is one of those questions where if I have an issue with my code debugging, it's going to be a massive pain. Cool. Okay, so question array questions equals new question array and questions. Equals new question I. So if this person got question J right, then questions J dot times right plus plus. This is equal to a 1. Sort the questions. Let's say we take 100 or 1,000 of those. Let's say we take 500 of them. Oh, we want the fewest right responses. So equals questions at I. We don't even need this array. What am I doing? Do we need this array? Probably not. Yeah, okay. So for int q equals 0, q is less than n hard questions plus. So look at all of the hard questions. For int p equals 0, p is less than n people, p plus plus. So if input at this person solved questions at q dot index, this is equal to a 1, then we want to say, oh, we need a people array. Person array people, person and people. Okay, in this case, people at p dot times right plus plus arrays dot sort people. And what now? Yeah, we want the person who got the most answers right. So oh my goodness. Let's try it. Are these both open? Can we see them? They're both visible. I guess we could just use the... Oh, there is no generator. I guess we could generate our own stuff. if we wanted to see. All right, so we're decent, but not good enough. So yeah, let's definitely just generate our own stuff. Cool. Yep, okay, and then static int real ants. All right, cool. So we have that, okay, so we need to do this generation. Let's make these static for convenience. Number of people by number of questions. We've got our random. All right, so if real answer is equal to the cheater.index, then correct plus plus. All right, so real ants equals random.next int and people. So we now have our cheater. For p equals 0, because we'll send people p plus plus. Okay, so IQ and then difficulty, number of questions. Then difficulty is the same thing. So this is number of questions, then difficulty at I equals the next double times 3. Yeah. All right, so static double sigmoid double x. What did they say this was? Turn 1 over 1 plus math.pow math.e to the x, or minus x. Okay. Yep, that should be a double. I guess we'll just do 1.0 just to be safe, but Yeah, it should be fine there. Cool. All right, so we have that. That's all working well. Okay, so we need the chance we get it right. Double chance right equals sigmoid of what? Sigmoid of intelligence versus difficulty. IQ at P. Oh. IQ at P minus difficulty IQ. Okay. Boolean right equals random dot next double less than chance right. To return at PQ equals right. If we're right, put a 1, otherwise put a 0. Okay, cool. So if we're the cheater, P for the cheater, and if random.next boolean, then to return at PQ equals 1, always. Okay, let's do 100 tests. We get 53% of them right. So, okay, that's not good enough, yeah. Cool. Maybe, let's jack this up. Maybe we do 1,000 tests. Okay, so let's do some analytics here. It's unlikely that we can just tune this to be better. We probably need to look at the yeah, so we probably need to look at the small, or like the easy problems. But we might be able to tune this number. %. That's terrible. What if it's 100? Then what do we get? That's actually so bad. %, so not a significant improvement. Yeah, what if instead we make it 1,000? Okay. 1,000 is 34% too. Okay, what if we just do all of them? Yeah. So if it's all of the questions, now we're wrong, right? So now, yeah, now it's probably not going to be right. It's probably going to get pretty low. Because there are a bunch of easy questions here. So it looks like it's increasing as we go down, but it's probably not super helpful. Okay, so if we get less than half of the questions right, we should throw those people away. Yeah. Okay, so yeah, so what are we interested in here? Maybe like partially how many times the cheater gets it right. So you get 75% of them right. That's pretty obvious. Okay, what if it's -3? And we get 55% very consistently. Okay, so we can throw out all of the people who get less than 53% of the questions right. If our intelligence is 3 and we don't do this part, then what would this be? 88. Okay. All right, so let's do these numbers, see how much room we have to play with. So a really smart person gets 88% right. Maybe 0.45% right. The dumbest cheater will get 55% right. What would the smartest cheater get? All right, so yeah, if the person gets over let's say over 90% right, then we know you are a cheater, because that's not really possible if you get over 90% right. So then what's the intelligence? Let's do like a manual binary search here. What's the intelligence you need in order to get 90% right as a cheater? Two. About a 2.2. Yeah, okay. So if you get a 2.2, then you're going to get the most easy questions wrong. Yeah, we need, I don't think this is going to work because like this 55% is very low. Yeah, like a 2.2 intelligence is like kind of smart, but it's not smart enough, I don't think. Could be that suspicious. So we need like the questions you get wrong need to be unpredictable. Yeah, so the average position of the questions you get wrong will be lower. Right. Because you're going to get hard problems right. Yeah. Or questions you get right. Questions you get wrong. I guess maybe the questions you get right are more interesting. No, because we're dealing with comparatively smart people. Yeah, so the questions you get wrong are more interesting. Okay, so Alright, so this is in a method. Cool. All right, so Yeah, so let's say your derp is yeah. Percentage of people who get a question right when I get it wrong. Okay. Yeah, okay. All right, so for each person, if okay, so we want to count, yeah, n wrong will be n questions minus p dot n times right. Okay, so Cool. Got 100% of them right. Okay. So we should be good there. Let's read input. What's going on here? Security. Security is unhelpful. Okay, print that. Don't print that. Oh, no solution, huh? Nice, got him. Yeah, I think this is like a very likely to, like, let's just look at this and see what the actual likelihood is here. So let's do the generation. This don't print the number correct at the end. Yeah, okay. So let's do 1,000 cases. See how likely we are to get one of them right. Oh, yeah, we can have this. We'll let this run for a bit, but looks like we're over 99% accurate. Which is quite good. We can probably tune the numbers to make it even better, but yeah. Cool, cool. All right, very fun. And then last problem is median sort. Okay, so yeah, I can do all of them except this last 10.1. I don't know how to do the last 10.1. Yeah, so you need to do better than that. It's close, it's close. So you have to do, okay. Yeah, so how do you do this median thing better than just guessing? If you pick 3 random elements, they tell us the median. Yeah, so then you have like some range, some known element, this, and then a whole bunch of other stuff. So if we pick like 2 more things with this, if they go to different sides, we just have to see which side we're on. Like if they go to the same side. Well, let's say we have this. Okay. So now if we put U, U, and U together, if this gets put here, then it's somewhere in this range. Or it gets somewhere in this range or somewhere in this range. So for our binary search, we can improve it. Yeah. The binary search we can improve by making this like a base 3 binary search. So we find like 2 positions that are like as close as possible to splitting it in half, or like splitting it in as small ranges as possible. Okay. Gotcha. So we can do this one as well. All right. So what does input look like? Man, this is very long input. Okay. Initially, the judge will send you the number of test cases, the number of elements in each case, and the total number of questions across all test cases. So int we don't get, so I guess the one benefit of interactive is we don't need to print the case number thing. Okay, cool, awesome. So we have this. And then what next? For int I equals 2 less than n I plus plus. Is n always small? N's at most 50, okay. All right, cool. So have I and then pass in fs. At the end, we just print this. Okay, initially it sends that. Program must print it. Okay, so you can either print 3 lines or you can print n lines. Okay, so yeah, it's 1 if it's correct, -1 if it's not. So we can print our answer. Now we just need to add to some range. Okay, so static int array add, or I guess, yeah, static int get target index, int array have to add val var. Okay, what now? So target index, the L is 0, tab.length plus 1, also fs, and then we want to build the result. Cool. So I think we should be fine here. So now we just have to build this recursive method. And I think that's it. Okay, cool. All right, so yeah. So if L is equal to R, return L. Okay, otherwise we have a bunch of these places. So we want to get like the first third and then last third of them. So this is like M1. M2 equals okay, so int n pivots, or like n splits equals rightmost pivot minus leftmost pivot plus 1. How does this work? Okay, so Okay, so good. So int p1 L plus n splits over 3 R minus n splits. Okay, so we have these two split points. Gotcha. All right, so ask about to add have at M1, have at M2. So if the median equals A, have an M1, then get target index, have to add. What's my left index? Stays at L. This equals M1. Yes. Else if mid or median equals have at M2. Okay, so this is M2 and this is R, or M2 plus 1. Otherwise, return from M1 plus 1 to M2. I think that's it. I think we're set. All right. So, one test case, 5 elements. We don't care how many questions you ask. 2, 1, 2. That's not right. All right, so debugging time. Okay. Three, 1, 2. Let's say 2 is the median. 4, 1, 3. Let's say 3 is the median. 5, 2, 3. 3 is the median again. 4 is the median. Good. Okay. Let's try this. The fact this is hidden is kind of annoying. Okay, yeah, sounds good. Well, yeah, I'm pretty tired. Maybe we'll try this a little bit just to see, because I really don't know. So what's going on here? It doesn't look like there's any. Oh, we need an interactive runner. Okay. Python interactive runner, command line judge, command line solution. So I think this is what I want here. Okay. Did they give us an interactive runner? Testing tool. Okay. let's make a new folder for this. Okay, so we probably want to put this in our Java files, CodeJam interaction. Okay, so these two go in this interaction folder. Good, and then we'll copy this into interaction as well. So now this is just a matter of copying the right commands. So we want this here, interactive runner.py, testing tool.py, Java solution. Oh, Java, so this is D. Yes, you can. Why can you not? Testing tool.py. Oh, local testing tool is what it's called. Oh, good. So I'm set. All right. I think I used few enough queries. Oh, awesome. Right answer, it looks like, by a pretty large case, or a large amount. Fantastic. Cool. So I think that's set solved then. Yeah, I think we're set. So we should have this, and then we should have, well, we've got everything else. Yeah. Yeah. Okay. Let's view United States maybe. Who do I know from the United States? Geothermal. About. Nice job, Travis. Jonathan Paulson. I think I recall Jonathan Paulson. Yeah, lots of solves. It was an easy set, what can I say? I guess we'll see more when we have more information on median sort. Cool. All right, so that's all from me. It was a fun contest. It was a very long video. How long are we at? It was over 2 hours. Yeah, so it was very long. It's 4 a.m. So I should not be awake. So you don't take long naps at 6 p.m. Your sleep schedule gets super messed up. Anyway, okay, so yeah, we can go over solutions briefly. Yeah, for this, you literally just do the implementation, right? You do the implementation and you count. So it's very straightforward. So yeah, you find the index you're looking for, and then you reverse it. So this is just what the implementation is. You just implement it. It's pretty straightforward. In addition, for this problem, if you've got a checker now, so you can verify your answer. And this is also somewhat straightforward. So what you can do is you can say, write some method that solves the problem recursively. If you have n spots you need to fill up, and you need a total of k sums of the lengths of the arrays that you pick in order to flip, then this is one way of doing that solution here. So yeah, so the idea for that is, for this next element that you're going to place, you start by placing whatever the 1 in the array is, right? So you're going to place the 1 in the array, you're going to place it somewhere, and then the array that you have left over after you do that reversal is going to be the array with everything except the 1. So you place the 1 somewhere, it flips some range, maybe everything except the 1 is what you solve in the next step. And in that case, the minimum element in that array is going to be 2. So you can kind of solve the problem in reverse order like that. And I'm sure if you wanted to, since this recursion is pretty simple, you could also do it bottom up, right? And then you can not do it recursively, you could do it iteratively, and that would work too. Yeah, so the idea is if you can solve it for an array of size 1 smaller, you just take that array, flip the part you're interested in, insert the one you want into the position that you're interested in, and that's the array that you return. So that's the idea for that. I'll show you the more fancy code. Looks kind of like this. And then you can do a little bit of math to figure out the smallest and largest size array you can solve. So yeah, that's the idea for problem C. Okay, cool. On to problem B. So for problem B, if you're just solving A and B, or like test cases medium and small, the observation you can do is you can just ignore all the question marks, right? So if you just evaluate it without any of the question marks, then that's some valid solution, because you want to avoid paying whatever this patent cost is. You want to avoid infringing this patent or trademark or whatever it is. So to avoid infringing the trademark, you just have repeated C's and repeated J's. So you replace each question mark with what would be the thing before it. That's the construction that you would use. And that's the same as ignoring all the question marks. So that's some valid solution. That doesn't work if the cost can be negative, because in that case, you might want to infringe on the patent. So for that, you can do a DP. You can use dynamic programming. And here's what the code for that looks like. But the idea is we can do some DP where we store what is the last item we placed and what index did we place it at. And we can brute force what element we're going to place on the next index. So when we do that, we know what the cost will be. If we place CJ, there's some cost for that. And if we place JC, there's some other cost for that. And we can just take whichever one is better. Now, we also have to keep track of the fact that the next space might have a predetermined character, right? It might be forced to be C or forced to be J. And if we place the wrong thing, then that has like an infinite cost. So that's what this part is doing here. It's part of the DP. Otherwise, we just take whichever one of them is better, either placing a 0 or placing a 1. This is like a C, and this is a J. Yeah, so that's the idea, and that should solve the hard part if I'm understanding it correctly. So that's the solution to A, B, and C. Median sort was the next one. So there are a couple observations for this, a couple different strategies you can use. This is where the problems start to get a little bit more difficult. So one thing you could do for this is imagine you have the first, imagine you have just 2 numbers, right? You have a 1 and a 2. They can be in any order you want. But now if you're going to add this third element, there are 3 places it can be. It can be here, here, or here. So if you have the 3 elements and you know which one the median is, and you assume that 1 is less than 2, then you can uniquely determine where this third element you should add into, you should insert it into one of these positions. You can determine where you should insert it. So that's the idea for that. So if you have a bunch of elements, you can say, okay, let's say we're going to add some 4th element here, or some 5th element here. We can say, if we compare it to these 2 elements, if it comes here or here, we can say, okay, well, just put it here, or just put it here. Otherwise, we can compare it to these 2, right? And then we can put it here if we need to, or we can put it here if we need to. Otherwise, compare to these 2, and then we put it here or put it here. So yeah, by doing that strategy, we add order n elements, and each of those takes order n comparisons on average. So this will be like n squared over 2. That many, we'll ask that many queries in order to sort the array. So this works, but it's not perfect. And it will pass, I think it'll pass just the first test case. So that should be fine for the first test case where n's really small. For the second test case, 50 squared is going to be too big. So 50 squared will be more than 300 on average, so you won't pass the second test case probably. So to do that, what you can notice is if you have a whole bunch of places that you could insert this one element, right, so maybe you've got like a bunch of these things, maybe you have like 30 already inserted, and you're trying to insert the 31st element. What you can do is actually you can binary search which part it's in. So you can check these two here, and if you're considering inserting something, maybe you insert it here, or maybe you insert it on this side of the array, or maybe you insert it on this side of the array. Right? And you can check that just by doing one median query. So this speeds up our runtime from n squared to n log n, n log base 2 of n. Because each time we do one of these queries, we split we split like the places we might put this element in half. So it'll take log base 2 of n queries in order to place one element. We do that n times. So that should pass the second case here. For the third case, what you need to do is make the observation that these two places that we're considering placing it, we don't want them to necessarily be right next to each other. Right? By splitting it in half, we're losing some efficiency with how quickly we chop down in the range. In particular, what we can do instead that would be better than that would be if instead of doing here and here, like that splits the array basically into 2 parts. We could split the array into 3 pretty much even parts. And now, instead of it going from n to n over 2, we go from n to n over 3. So we approach an array of size 1 more quickly. That's the main idea. And that's like just a constant factor, and it seems to be fast enough. So yeah, here's the code for it. This just like, okay, so this add will have some array, it'll add one more element to the array, and then it'll ask a bunch of queries in order to figure out how to add it. So this will take about log base 3 of n queries in order to complete this method. In order to complete this, we do this like sort of binary search, but we split it into 3 parts before we do that binary search. It's different from a ternary search because in a ternary search, you cut off 1/3 every time you go down. Or maybe you could call this a ternary search, but it's like a variant of it because in most ternary searches, you cut off 1/3. You either cut off the left third or the right third every time. In this case, you cut off 2/3. So you might cut off the left and middle, you might cut off the middle and right, or you might cut off the left and right thirds. So this is like, it's not 2 times log base 3, it's just log base 3, which is better than a binary search, actually. Okay, so yeah, so this is just, I guess, some very careful logic on where we split it, because I didn't want to get it wrong. And this is one way of doing that. Cool. All right, so that's that. The last part is, or last problem, is this cheating detection. So this was a super interesting problem. I really enjoyed it. I feel like this is exactly the kind of thing that Python would be very good for, because there's a lot of like data analytics tools in Python where you can visualize this data, and being able to like look at a graph of this stuff and be able to type it quickly, I feel like that would be super helpful. Yeah, so I guess if you're expecting more problems like this in future CodeJam rounds, it might be a good idea to freshen up on your Python skills, your data visualization. But yeah, the idea behind this problem is you have a bunch of people doing this competition. Each probabilistically gets some problems right. You've got easier problems and harder problems, and then more stupid people and smarter people. But importantly, you have one person who's a cheater, and that person, 50% of the time, no matter what type of problem it is, that person will get the problem right. So the question is, can you accurately identify the cheater? For just a few points, you can identify them 10% of the time, or for test set 2, you want to identify them 86% of the time. I was able to get about 99.4%, but I can probably do better even, and you can probably get very close to 100 because I think if you tune stuff, you can get it very accurate. Not 100, of course, but you can probably get very close to 100. So what's the idea? So for test set 1, what you can do is just say, let's find whoever gets the most problems right. About 20% of the time, that person's going to be the cheater. So for test set 1, literally all you need to do is just see whoever gets the most problems right, we'll say they're the cheater. And it's that easy. Okay, for test set 2, you have to do some more interesting things. So you can, like, the cases that you'll get wrong are people who are very smart will get a lot of questions right. They'll get way more than 50% right. Like, you can be smart and legitimately get 88% of the questions right without cheating. If you have an intelligence of 3, if you're like 3 standard deviations above the mean or whatever, then you'll get the questions right 88% of the time. Now, that can be a lot better than what a stupid cheater would get. A stupid cheater can get it right only like 55% of the time if this cheater has intelligence -3 but still gets half of them right plus the ones he happens to get lucky on. So yeah, an intelligent person playing legitimately can still get way more problems right than an unintelligent cheater. And most of the time, like, the person who gets the most problems right actually happens to be someone playing legitimately. So what can you do about that? Well, one thing you can do is say, okay, so if anyone gets over like 90% of the questions right, they're almost certainly a cheater. Because even if you're super smart, you have to get really, really, really lucky for that to happen. So what I do is I say, okay, if anyone gets over 9,000 questions right, they have a power level over 9,000, that means they must be a Dragon Ball Z protagonist or antagonist or something. So we'll just stop this right away before we blow up the Earth. Otherwise, if everyone has a power level that's at least somewhat reasonable, what we want to do is say, who is very suspiciously getting questions wrong? So someone who is like stupid, but like smart, like they're not that smart, but they're smart enough in order to get hard questions right. So yeah, let me try again. Someone who's really smart will get almost all of the easy questions right, and then they'll get some hard questions right. So let's do a drawing here. So let's say like this is like the frequency that you get right. And this is the difficulty. So a smart person will have a graph that looks something like this. Right? So this is like someone who's smart. And then someone who's stupid will have a graph that looks like this. They'll get a lot of these right, and then they'll get like closer to none of these problems right. The thing is, for the cheater will have something that looks like this. Like, they'll have a lot or a decent amount of hard problems right. Right? So they'll get like this many hard problems right, and then they'll get maybe slightly more easier problems right, but it'll be something like that. So the cheater's graph will be very flat because they're always going to get 50% of the problems right of every difficulty. Whereas other people will get less and less, like fewer and fewer problems right. But the smart people, like someone who's really smart, will... Okay, yeah. Someone who's really stupid, even for the hard problems, they'll level off at about like 55%. But someone who's really smart, for the really hard problems, they level off at about 50%. So what we want to do is find this sort of discrepancy between this person who's a cheater, who has a pretty flat curve, and the person who's smart, who will get fewer hard problems right and then more easy problems right. What we can do is say, for the problems that this person is getting wrong, how like stupid of a mistake was it for this person to get that problem wrong? In my code, I say, how derpy was it? So if it's a problem that almost everyone is getting right and you get it wrong, that's a really derpy mistake. right? So like either you just like had a really off day when you got it wrong and like, oops, what can you do? Or you're a really stupid person, right? If you're a stupid person, it's okay to do stupid things. Quote of the day right there. So yeah, so like if you're a stupid person, it's understandable that you would get easy questions wrong. But if you're a really smart person and you're consistently getting easy questions wrong, that's a very suspicious thing. It's a good indicator you might be cheating. Especially if you're a smart person, you're getting, like, you have a very good score. You're getting a lot of easy problems wrong, but all of the people around you aren't getting problems wrong until those problems get really hard. So yeah, so basically what we can do is like look at the median difficulty of the problems you get wrong, and that can be your derpiness. And what we'll see is whoever the cheater is, they'll have a much lower, or I guess a much higher derpiness, right? They'll get, the questions they get wrong will be much easier than the people who score a similar number of problems correctly. Yeah. And I just like looked at the data a little bit and found that like there's like a 10 times difference between like the jump in derpiness between the cheater and everyone else. Yeah. So to actually do that, what I do is I say, what is the percentage of times each question is gotten right? And then I say for each person, what is their average derps, right? So for each question they get wrong, what's the percentage of people who got that question right on average? Then if you sort the people by how many problems they got right, you'll see a significant jump in derpiness at a certain person, right? So over this number, I guess 2%, that means there's some person where at this person, there's like a 2% increase in the number of people who get the average problem that this person gets wrong right. So for the problem this person gets wrong, all of a sudden, that problem got a lot easier. It got 2% easier for this person, and then it gets about 2% harder on the next person all of a sudden, right? And we expect this to be pretty level, right? The stupid people will get easy problems wrong. The smart people will not really get any problems wrong. They'll only get the really hard problems wrong. But all of a sudden, we'll find one person who's like, okay, this person on average is getting pretty easy problems wrong, but they're getting a good score somehow. And that's like an indicator that they're the cheater. So we find that person. Yeah, this finds about 99.4% of 99.4% of the time this will get the right answer. But I assume that it's just this number here and this 0.02, which I had somewhere. Yeah, this number here. So a combination of this 9,000 and this 0.02. I think if you adjust those numbers, you can probably do better. Maybe even very close to 100%. And then the other thing is like this 0.02 probably shouldn't be a constant if you want an optimal solution. It probably varies. But yeah, I don't think that's too important. That's the idea behind the solution anyway. Cool. So this is an insanely long video, and I don't know, maybe it was useful, maybe not. But I guess I'll upload it to YouTube anyway, and I won't post it till the contest ends. All right, thanks for watching. There's no way you watched the entire 2.5 hours. It would be insane if you did, because some of it was super boring. Some of it was just like me experimenting with the data on E. But I thought it was a fun contest. Hopefully you did the qualification round yourself, and if you did, I'll see you on round 1. Bye.